Good morning. Back to Hunky's study again. Today, I'm going to talk about surface area a little bit. Before we actually talk about surface area, I'm going to talk about arc length. So suppose I give you some curve in three-dimensional space. So there it is, curve C. And you want to find the length of C. How do you do it? Well, the first step is you parameterize C. Or maybe the first step is just to write down the answer. The answer is the integral over C of the one function. There is the answer. But how do you actually compute this? Now, the first step is parameterize. And so a parameterization of a one-dimensional shape, like a curve, has one variable, but it might be t squared, t cubed, 0 less than or equal to t less than or equal to 1, something like this. And now you can change this into the integral of 1. And we're going to be integrating from t is 0 to 1. So we're going to use our parametric variables to integrate dt. And I left space because this is not correct. This will not give you the arc length if you just do this. This just gives you 1. What's happening here is that this parameterization tells you how the unit interval is stretched in order to make it fit on this curve. So there's an expansion contraction factor, an x-con here, that you have to compute. And we already know what that is. It's the speed. So you take the derivative, c prime, and you take the length of c prime. And this is the expansion contraction factor. So now when you integrate this, then you get the length. This is the first step of a huge battery of computations. And the second step is surface area. So now let's take a look at a surface area problem and see how it's the same. So I give you a surface, some surface in three-dimensional space. So let's take a shape like this. And I have to delineate it in some way. So somewhere on the x-axis, we have to delineate what part of the shape we want to look at. An entire bowl, if it goes off to infinity, will have infinite area. But maybe this is just a rectangular region. And we want to find the area, the surface area of this paraboloid over this blue rectangle. So to do that, we'll bring these up to the curve. Maybe that's there, maybe that's here. And this will be over here. This will be maybe here. Something like this. We'll get some shape like this, and we want the surface area of this shape. How do you do it? Well, the surface area of this surface S that I defined here, maybe we should say that S is the graph of a function f of x and y equals, let's see, 3x squared plus 2y squared over, let's say, 0 less than or equal to x less than or equal to 1, and minus 1 less than or equal to y less than or equal to 2. Kind of correspond with what I've got. So we've got an elliptic paraboloid lying over this rectangle. We want to know what the area of S is. And since this is a surface, the area of S is the surface area, and we know how to do this. This is the integral of 1 over S, and it's a dA integral. You're looking for area, so the book puts 2 integral signs down. But you know, after you're in like 6-dimensional space, this gets tiresome. Usually just 1 integral sign, but you have to know what the dimension is because of S. So this is the answer. This gives you the surface area. The question is, what number is it? What does this mean? How do you do this? And the first step is, again, parameterize. This surface. And I gave you this one because you can use the so-called graph parameterization. It's the easiest of the examples. So if xy is down here in the base, a point above it on the surface is the point x, y, and then 3x squared plus 2y squared. And so this is the function that controls it, mapping 2-dimensional region into 3 space, and 0 less than or equal to x less than or equal to 1, and minus 1 less than or equal to y less than or equal to 2. The way I've drawn it here, this blue rectangle has a place in the domain of the function, which is fine. That's the graph parameterization. But you can also think of x and y here as separate, and this actually can be helpful. So y goes between minus 1 and 2, x goes between 0 and 1. So this function s of xy takes points from here and maps onto the yellow surface. And so this is a parameterization. The next step after the parameterization, I need to erase some stuff here. Maybe we'll erase the picture. The next step is to have this integral reflect the variables that you're using here, x and y. So this will be equal to the integral, and x will go between 0 and 1. Y will go between minus 1 and 2. X is first, y is second. You're integrating the one function, but you've got an x-con here, an expansion contraction factor to compute. And the expansion contraction factor has to do with this function s, the parameterization itself. So the next step is to compute this x-con. And let's see how to do that. So just like with curves, this is dependent on the derivative. The derivative here will have 3 rows, 1 for each coordinate. So it's got a derivative for x, for y, and z, these rows. And we've got 2 variables, x and y. They happen, because it's a graph parameterization, they happen to be the same as this, but this is what doesn't always happen. And so this matrix, this 3x2 matrix, the derivative of x with respect to x is 1, x with respect to y is 0, 0, 1 here. And now we've got a little work to do. Derivative of z with respect to x is 6x. The derivative of z with respect to y is 4y. So here is the derivative. So this is the first step. And the second step, the x-con is actually the square root of the sum of the squares of 3 determinants. And these determinants are determinants of the maximum size matrices contained in this derivative. So this is a 3 by 2. So the maximum size square matrices are 2 by 2. Here's one of them. So that determinant goes there. Here's another one. The last one, another color here. The last one consists of the first row and the last row. So 1, 0, 6x, 4y. So this is not a speed, but this is the expansion contraction factor due to this parameterization. So when we compute this, that's what goes here. So this gets plugged in right there. I'm going to do that. So we get the square root. This is 1. This is 6x squared, so 36x squared. 36x squared. And this is 4y, so 16y squared dx dy. There you go. This is the surface area of this paraboloid, elliptic paraboloid over this rectangular region. Are we good with this? Speak up if you remember mine. All right, so this is example 1. This is the easiest case that we will have. So I'm going to erase this and we'll try another one. And let's not change the function. And I'll keep that, but I'll change the domain here. Let's say over D, where x squared plus y squared less than or equal to 1. So now again, we're looking at an elliptic paraboloid. And this time we take a circle centered at the origin down here. And we want the surface area of the paraboloid, of the elliptic paraboloid over this disk. Now you could say, well, you just cut it straight across. But if you cut it straight across, then you would get this ellipse. And this is a circle, not an ellipse. So this is, if you look at the actual piece, it will look something like this. And we want the area, the surface area of that little piece down there. All right. So let's go ahead and do it. The answer is this area of S is equal to the integral of the 1 function over S. Now we're at the point where we have to parameterize. And there are sort of 2 ways to do this that are apparent. The first one is almost like what we did before. So S of x and y, I'm going to use the graph parameterization. S of x and y will be x, y, 3x squared plus 2y squared. But what gets a little more complicated is the domain. So if we are going to integrate this with respect to, let's do it the other way this time, y first and then x, this will be a double integral. Y will go between minus the square root of 1 minus x squared and plus the square root of 1 minus x squared. These are always y equals. When you're solving, you can remember what to solve for because everything here is a y. you're integrating the 1 function, and then x will go between -1 and 1. So this will do it, but you need this x-con that we found before, the square root of 1 plus 36x squared plus 16y squared, if I remember right. This is dy dx. That sets it up. Again, a graph parameterization, a little more complicated because of these limits. And so this is one way to do it. On the other hand, there's a second way to do it, and this is the second parameterization. And this one is set up to use polar. This is well established using polar coordinates, and I'll try to show you the advantages. So here we're going to let x equal r cosine theta, y equal r sine theta. And so our parameterization will be S, where the variables are now r and theta, but it's going to be the same surface, r cosine theta, r sine theta, and then f of x and y. So this will be 3 r squared cosine squared plus 2 y squared r squared sine squared. So it's a little more complicated, but the good part is that r is between 0 and 1, and theta between 0 and 2 pi. This is big advantages when you're computing. And if you're using Mathematica, you can use implicit function or implicit region to define D. But in higher dimensions, you don't have Mathematica to work for you. And this kind of parameterization becomes an important tool. Now, what we are doing here is we are in the r theta plane. R goes between 0 and 1. Theta goes between 0 and 2 pi. And this function, s of r and theta, maps that rectangle exactly onto that piece of surface of the sphere, of the paraboloid, above the graph of x squared plus y squared less than or equal to 1. So now this function maps this rectangle onto this exactly. So it takes it, it folds it, it bends it, and it makes it fit there. And this computation finds the area. I didn't do the computation yet, but these computations find the area of this figure. This integral over 1 now, if we use the polar one, becomes equal to the integral. R goes between 0 and 1, theta goes between 0 and 2 pi, the 1 function times the expansion contraction factor. The expansion contraction factor is the derivative of, is the sum of the squares of the maximal 2x2s contained in this derivative. So we've got another derivative to take. We want to take the derivative of this. You can use the chain rule actually, but I'm going to do it from scratch. So this is again 3 rows, 2 columns. You have an x, a y, and a z coordinate, x, y, z. And you have an r and a theta. These are just helpers these aren't part of it. This just tells you how to do it. So this is the derivative of x with respect to r. So this is cosine theta. This is the derivative of x with respect to theta. So this is minus r sine theta. This is the derivative of y with respect to r. So sine theta, r cosine theta. And now there's some stuff to compute. The derivative of z with respect to r is 6r cosine squared theta plus 4r sine squared theta. Then we got one more to compute. So this expansion contraction factor, when we're going to compute it, has, again, the sum of 3 determinants squared. The first determinant is this guy here, cos theta minus r sine theta, r cos theta. So this will just turn out to be r squared. And then, and that's this determinant. And then there's the determinant of the second row with this. So sine theta, r cosine theta, and then these two, and the same thing here. I mean, this next one is cos theta minus sine theta. And then whatever is here goes here. So the trade-off is that you're integrating over a very nice region, rectangular, a little more to compute when you have the expansion contraction factor. There's one more little piece I thought I would show you. There are a raft of problems like this, and I'll give you some from the book, which are graph parameterizations. They can all be done that way. But I'll give you a few others that are not defined that way to let you test the more general theory. But I wanted to do an easy example. We'll take a linear transformation from r squared to r cubed. A linear transformation, that means L of x and y has got a matrix representing it. The matrix will be 3 rows, 2 columns, this matrix right here. So something like A, B, C, these are constants. So doing a little linear algebra, linear transformations, this can have a constant on it to it. It's going to work the same. But what I wanted to show you here is that if you take L prime of x and y, the derivative of a linear transformation, you get the matrix representation. So the derivative of any linear function is the matrix representation. So if this is mx plus b, then you can think of the matrix representation as the multidimensional slope. Okay, so now what will happen is then your expansion contraction factor does not at all depend on x or y, because it only depends on these constants. So it's the square root of AB CD squared plus, this is determinant, plus the determinant of CDEF squared plus the determinant of ABEF squared. And this will be constant, maybe 7.12. I mean, I just want you to know that this is a number. And I want you to see what this number tells you, because you can see it is an expansion or contraction factor, in this case expansion. And I'd like to sort of show you in what sense it's expanding. So here we have the plane. We're mapping into 3 space. L is our mapping. Because it's a linear transformation, L will pick up this plane and put it somewhere here. If it's a linear transformation, it will go through the origin. If it's a linear function, it doesn't necessarily go through the origin. It picks it up and puts it here, but in the meantime, it can jam it around and shift it in some way. But if you take any shape here, so we'll take shmoo. So if we take this shmoo shape and suppose that the area here, this guy has area, the area of this figure is 3, then this guy gets smushed around, but this guy will lie in the image plane. He can be stretched out and distorted some. This is supposed to fit in the plane, but L transforms this guy. He stays in the plane, but he gets shifted. But the area of this guy so if you take area of L of shmoo, this will be 7.12 times this area. So no matter what area you take here, this one here, this has some area here like 4. It doesn't look like 4, like 2. And the area of the image will be 3 times 2. So this is really the expansion contraction factor. If this would have been 0.712, then the area of the images is always about 3/4, 0.712, times the area of what they started to be. So this would be a shrinkage. If this is less than 1, if it's equal to 1, all areas remain the same. If it's more than 1, all areas get expanded. So this really is an expansion contraction factor. Okay, so I will see you tomorrow in class. Hope everything's going well. I want to remind you that at 3:30 today, there is a pretty cool event in the math department. You can look on our MSCS website and get links to it. And in those links, once you get onto those links, you can find out a bunch of information about the courses we offer, the opportunities that we offer, and there are a lot of really cool ones. So I encourage you to take a look at them. 3:30 today. In any case, see you tomorrow.